Hey there, Math 126 fans. Going to finish up this reflection of Exam 1. This is going to be about page 4. This is about measurement and working with curves in 3D. The first question was just a straight computation. Compute the curvature at t equals 0. About 65% of the class got this completely right. There was a small percentage, maybe 10%, that didn't know the formula or wasn't quite prepared. This particular question is on, I think you had to compute about 5 or 6 of these in the 13.3 homework, and then it's on all my old tests. So that's something we can prepare for in the future. Know your formulas, know your computation. Mostly this was a chance to use this. A small note, which is we should have been immediately taking the derivative and then immediately plugging in 0. A few people tried to compute the general formula, but my advice in class was, when we were reviewing, I should say, was to plug in 0 the moment you get there. Do remember that when you do a cross product, you can check it against the previous pieces. And again, the goal is just to say, what surprised me about that? Was I not expecting it? How did I mess up? Now, quite a few people didn't simplify. That was fine. I gave full credit. A few people forgot the cube, things like that. Preventable mistakes, but I just wanted to say a little bit visually. Just so this is just a side part. You don't need to listen. You can skip ahead if you just start having questions about other parts, but I think this will be interesting. So here is this curve. This is this thing moving along it. Time 0 is right here. And right at that moment, we're going in that direction. So we know how to find all those things. Those are kind of the fundamental pieces we've been playing around with. So I was asking if you could measure how much you're turning there. So we got the radius of curvature, we got the curvature was 1/10. So I'm going to expand my window so you can see the calculation, just because this is the point of this, is to learn and understand. All right. So we computed at 0. Ooh, I have a mistake. That can't be right because that doesn't match up. Did I type in my equation right? I did not. Darny darn. This is 4. I think this was a different version because before I made a certain function and then I made it come out nicer. I see now. So there we go. That's a little better. Let's zoom in. I made the numbers come out nicer after I made this visual. So when we get to 0, we get 0.1. But what that means is if you were to fit a circle that perfectly fit there, the radius would be 10. We call it the radius of curvature, and it would be that circle. And last quarter, I spent a bunch of time trying to figure out how to compute that circle. That's the circle that's tangent there. You actually can make a sphere from that, and that's called the osculating sphere or the kissing sphere. To osculate means to kiss, but that's it. You can see that it's turning sharpest, like somewhere over here. And then it's a little bigger, and then it turns sharp here, then it's here. There's a couple spots where it's sharpest. So I find the radius of curvature to be more useful, but that thing you're computing, that curvature, has value. That's the point of me showing you these pictures, the fact that you can compute it. Yeah, it's not the greatest to compute, but it has value. It's worthwhile. We're computing something interesting for measuring how much a curve curves. All right. Next piece. So I hope that was fairly quick. This question, I was thinking of this homework question. So in your homework, you had this question that said, find the point on the curve when the tangent line is parallel to this other plane. So that question, again, this quarter, I'm removing some homework questions, adding a few. That's one I added, but you also had 2 other questions that had to do with tangent planes. So at some point, you had to figure this out. So as we go through this question, think about how did you do that homework question? How did you figure it out? Because that was the challenge I put here. Is I was like, okay, I'm going to take that homework question, make it a little simpler, and put it in the exam and see what students do. So you can be aware that kind of in 2 spots in this exam, which I've already mentioned one, that was the only place where the challenge was that I took something directly from homework that maybe isn't in as many exams, and I said, here you go. How well did you understand the homework? So that's a tip for you, which is if you know all the homework really well, you're going to be ready for these tests. Okay. So anyways, this question was about the tangent line. I wrote my solutions. I have a bunch of words just kind of explaining. But the idea was, if you were going to find the tangent line for this, you would need the derivative. The derivative would go here in your tangent line. And the location, sorry, I know I'm doing a bad job here with my screen. Okay, and so this would be your derivative. I called it A here just to emphasize we're looking for a particular time when that tangent vector forms a line that is parallel to this plane. So yes, it's a little bit to think through, except that you had just done that in homework, in the 13.2 homework. So you had to have these thoughts already. This plane has this vector 1, 1, 0, and that vector is normal or perpendicular. So again, if you have two things that are parallel, and then a vector that's perpendicular to one of those things, then the vector is also perpendicular to the other. So often, I know I will get questions on this. Students will say, why did you say perpendicular? The question says parallel. And then I'll answer it, and the next person in line behind them in class will say, why did you say perpendicular when the question says parallel? And then I'll answer it, and the next person in line will come up and say, so please, listen now, this is your chance. You can always ask, and I'm always happy to discuss again. But if this line and this plane are parallel, then this vector, the direction vector for the line, must be perpendicular to the normal vector. So once again, remember that the normal vector for a plane is perpendicular to that plane. Yes, that was a bit to think about, but we had already had to go through that process in the homework. Okay, so the question really was saying, when is this perpendicular to the derivative vector? So you didn't really need to say A, you could have said it directly, and that came out really nice because the derivative vector was -4 and 2t, and that the third part didn't even come in because this was 0. So in order to check the two vectors are perpendicular, the dot product has to be 0. We did use that quite a bit. So that means that the t had to be 2. And then the question, a couple people kind of dropped the ball right at the end. The question said, find the point on the curve when this happens. A few people plugged it into the derivative and found the tangent vector and lost some points. But you had to plug that into the point on the curve. Okay, so let's just show you visuals of that too, because I'm kind of into this. Here is the equation for that plane. So a natural question is, when are you parallel to it? Is there any time when your tangent line is parallel? Not the most interesting question, but like that homework question. So let's just show you let's get rid of the oscillating circle. Okay, good. Let's show you the tangent vector again. So if you watch that tangent vector, it currently is not parallel to the plane. In fact, it looks like it's going right into it. If you keep going, it's still not parallel, and we're trying to go to where it's parallel. So when is the tangent line going to be parallel? And I meant to do this, but let's draw the tangent line as well if you prefer to see the line. I'm just showing you the vector, which is all that really matters. But I'm going to draw the tangent line here. So let's see, this plus this times t. Let's make this go this to 10, -10. Let's make it orange so we can see it. So there's our tangent line. Notice it is not parallel to the plane yet. Let me just get rid of this. So the question is when? It hasn't happened yet. None of those are parallel to the plane. Does it ever happen? Wait. Ooh, that looks like it's almost there. Almost parallel to the plane, maybe not quite. Ooh, right on. At what time does that happen? Well, it's when t is 2. I can show you this here. T is 2. So experimentally, I just found it. But the point is that at that moment, it's perpendicular to the vector 1, 1. Okay, I hope you're finding this interesting. Again, I'm showing you the visuals to show you that this actually matters. If you're going on into a course where you're working in 3D in any way, it's nice to have these tools. In addition, I hope you're seeing that the questions here are just like the homework or old exams. So I'm trying to give you more guidance on how to prepare. Make some notes to yourself about adjustments to how you approach the homework and studying. And I think we all can do a lot better on the second exam and finish the quarter strong. All right.